Welcome back to Code Meets World, and today we are looking at LeetCode problem number 50, which is called power of x to the n. And simply put, we need to implement the power function from scratch. So basically we need to raise the number x to the power of n, but we need to do that without using the built-in math function that's provided in most languages. So let's jump down to the whiteboard, and I've just copied the examples from the problem. So we can see in the first one, we need to take 2 and raise that to the power of 10, which would give us 1024, and same for the others. You can see that we might encounter negative values for either x or n, so we need to make sure we handle that too. So before I do anything else, there are several ways that we could actually solve this. The first of which I already mentioned, which is to just say, this is in Python, math.pow xn. This would probably work, and the NeetCode would probably accept this, but this is not in the spirit of the problem at all, because it's just using the built-in function, which we don't want to do because we want to actually create this from scratch. Now there's something else we could do, which is to use loops to make this work. So raising something to the power is basically just multiplying that number by itself n number of times. So we could say, we could have some solution variable and set it equal to 1, and then we could loop for I in range n. So however many times, if we need to raise it to the power of 5, we need to loop 5 times. And each time we just say solution equals solution times x, where x is the number that we're raising to the power of n. So this would also work, but we might encounter some problems with runtime and possibly memory if we do this for a large enough value of n. For instance, if we have to loop, I don't know, billions of times, that might not be able to work. It might throw a memory limit error or a runtime error. So we also want to try to find a solution that doesn't use loops at all. So there are other ways you could do this, I think, such as bits. You could also use recursion. I'm not actually sure how to do it using either of those methods, but I'm quite sure that we could work out a way to make that happen. But the way that I want to talk about doing it is actually with math. So if we write x to the n, and I'm just going to set that equal to itself. And if you've taken a mathematics class before or completed any proofs, you'll know that we can just manipulate both sides of the equal sign so that they stay equivalent to show or to prove that one expression equals a different expression. So we'll start out with this, which is true. Those sides are both equal. Now, as an aside, and I'll do this each time I use a mathematical concept, you might know that if you take e to the power of log x, these actually cancel out, and you would just be left with 1. So what I'm actually going to do here is take the one side of this, so this side, and I will raise that to e log xn, and the other side I'm just going to keep is xn. These are completely equivalent because the e and the log could cross out. Those cancel out mathematically, and we would be left with just x to the n on this side. So these two expressions shown here, completely equivalent. So now there's another property of logs that we need to use. So log of something raised to a power, we can take the power, so in this case the n, and we can bring that out front to here, and those are equivalent. This is a property of logarithms that you may have seen before in mathematics. So using that rule, we can again keep the left side the same, and we can change the right side, e to the power of, using the rule shown in red, n log x, like that. So the reason I did that last step is important, and that's because right here in red, we couldn't just stop here because it still is using an exponent. It still has x to the power of n in the equation. We're trying to completely get rid of that so that we don't have to compute an exponent or use a loop of any kind. So that's why I completed the third step here, which was to take the n and bring that out front using properties of logs. So now we are left with this statement here, and these are both equivalent, these are the same thing, but it showed how we can rewrite x to the power of n in terms of e raised to the power of n log x. Now there are still a few things we have to consider, like what if x is negative, or what if n is negative? X being negative is important to consider because you can't take log of a negative number. So that's something important we have to think about. And if n is negative, that's a different computation because taking something to the negative power is the same as taking the inverse of the number you're raising to the power and then making the power positive. But we're going to talk about all that when I get to it in the code. Okay, now we're going to take a look at writing the code based on the math that we just proved on the whiteboard, which I'm showing on the screen right now so we can reference it as we go. So let's start out with what would happen if we just implement the equation that we solved for, which is shown in the white box there on the whiteboard. So what if we just said math.exponent? Now, if you haven't seen this before in Python, if we use math.exponent, this is going to take e and raise it to the power of everything in the parentheses. So that way we can just do, looking at our equation, n times log of x, not to the power of, n times, like that. Math.exponent n times the log of x. So this is the equation we solved for, and I'm actually going to go ahead and run this just to show what happens, because this is technically all we need, but we have to think about a number of other cases. So as you can see, that actually solved all three test cases. But if I submit this, we should find that it doesn't pass everything. Yeah, math domain error. This is likely because x is negative, and actually, yeah, the test case right here is showing that x is negative. So we need to think through what's going to happen in the case where x is negative. And I might just show this on the whiteboard. So if x is negative, so for instance we get negative 2 to the power of 2, that should just be 4, right? But the problem is that in our equation, we're going to end up having to compute log of negative 2. You can't compute logs of negative numbers. In fact, they're undefined. This is undefined. I don't think that's the right abbreviation for undefined. I think it's something different, but that's undefined. So when we see a negative for our value of x, we need to adjust. So what could we do? So if x is less than 0, we need to do basically two things. We need to first solve this equation for x being positive. So I'll say like solution equals, we'll take log to the negative x, because this will give us the same answer But then we just have to think about whether our final solution should be positive or negative. So for instance, if our value of n is even, our solution can just be positive, right? Because we're multiplying a negative number an even amount of times, so the negatives will cancel out. But if instead we were raising this to an odd power, that's going to be negative times negative times negative. These two will cancel out, but the final answer is going to still be negative. So in that case, so basically I'll write this in. We have to say if n is odd, we need to make solution negative. And here's how we can do that. So we can say if n modular division 2, if that's 1, meaning we divide it, we see how many times 2 can go into the number, and if there's 0 left over, it would be even. But if there's 1 left over, it would be odd. So if it's odd, we can return the negative of solution, like that. Then let's see if that works for this test case. First, let's run it. On the test cases, now let's submit it and see. I think there's still a few other things we need to do until this is correct. So yeah, we still have a math domain error. So I think that's because, in this case, x is less than 0. It's not odd. So in the case where n is even, here we just have to return solution, right? So in the case where x is negative, we make x positive and solve with the equation. Then if it's even, we just return whatever we get here. But if it's odd, we have to make the resulting solution negative. So that should now pass the test case that we were failing to the left. And as you can see, we're now failing a different test case, which is when x is 0. So this brings me to another thing that I wanted to talk about. If we're given, for instance, 0 to the power of 1, or 0 to the power of anything, this is actually undefined. So in our case, we just need to return 0. So I'm going to add that up here. So if x is 0, we're just going to return 0. And that should pass the test case that we just failed. And as you can see, by simply fixing the case where x is 0 and the case where x is negative, this mathematical solution handles everything else. And the runtime is actually really respectable. And we did all of this without using math.pow, as well as not using any sort of loops, which I think is pretty neat. And all we needed was that one simple proof, which I have on the screen in the whiteboard, in the box there. Just a 3-step proof, and we can do this with math alone. So I hope that makes sense, and I will see you in the next video.